Hello physical science student, welcome to another momentous video because this is your second video. This is video 1.2 in atomic structure, and this one we're going to look at the atom. Now a lot of you will already know about the atom, but this is all about making sure that we're all on the same page in terms of what we know about the atom, and so that we can then move on to more complicated things. But first off, we'll have to do a little bit of introductory stuff. So our understanding of the atom has changed through time as we've learnt more and more. If we went back to the last video, we were talking about the kinetic theory of matter. We had these invisible particles. Now we now know those invisible particles are actually atoms. They could be ions, or those atoms could be arranged in molecules, but they're made up of atoms. And we know that atoms are actually made up of other things as well. But the kinetic theory of matter still stands because it's a convenient explanation of change in state and why we have different substances have different properties. Right, so let's go to the atom. And what we've got here is a little timeline which goes through the history of atomic theory. Starting down here at let's say that's around 400 BC, and this is time 0, and then this is us moving towards the present day, which is about here. So you get the idea. So not much happened for a long period of time, and then it all got very exciting as we discovered more and more. So there was this guy, he said that matter was made up of these tiny particles called atomos, and that's what he looked like apparently. And that was at 400 BC. And then there's a long time before anyone actually made any other major discoveries. There were the Dark Ages, and there was a lot of time when science didn't really get much of a play. But Isaac Newton in 1704, he said the universe is made up of small solid masses in motion, which was pretty close to what we were thinking. Then there was a guy called Dalton, 1803. He had the atomic theory where elements are made up of tiny spherical particles. He called them atoms, and atoms of one element are identical, while atoms of different elements are different. So people were starting to classify atoms according to what they are and what substance they were. And then this guy, Dmitri, he started organizing what we know as the periodic table, and people were organizing it before, but he came up with the one that people have accepted nowadays and use pretty much. Now we were still discovering things about these atoms, and J.J. Thomson discovered that there were negative particles, what we would call electrons. He hadn't called them electrons, but he thought they were negative particles, and he proposed what's called a plum pudding model, and we'll have a look at that shortly as to what that looks like. Oh, there it is there. And so his view of an atom was that this is what the atom occupies in space, and you must have these negative particles sort of stuck like cherries in a pudding, scattered around. Then there was Ernest Rutherford, New Zealand's most famous scientist. He said that the positive charge is not like a pudding, and so in the plum pudding, if you had these negative charges, all the plum must have been roughly positive. And Rutherford said, well, no, there's no pudding. The positive charges are actually concentrated into their own particles. He didn't necessarily know that they were particles, but he said we'll have this thing called the nucleus, which is positive, and most of the atom is actually empty space. And Niels Bohr, who had Bohr's orbital model, he started, and this is 1913, so things are starting to happen. That's where electrons are in their own unique orbits around this nucleus. Something like that is a common way of drawing it, and we'll look at that in a little bit more detail shortly. Moseley said the atomic number of an element is equal to the number of protons in the nucleus. So we're now defining what an element is, and then things started to get weird, as you can tell from the hairstyle, when quantum mechanics were introduced. And we're not doing any quantum stuff in physical science. That's when things start to get weird. Atoms or particles are present or not present, and appear and disappear, and apparently travel faster than the speed of light, all sorts of things. And then we discovered the neutron, which took a long time to discover because it doesn't weigh much and it has no charge. But people had proposed about its existence, and then it took 1932 before it was actually discovered. So let's just look at it through another way. The theories of matter, the Dalton model. Basically, way back, people just weighed different things, and you could have pure substances. You could have pure sulfur, you could have pure oxygen. People could find some pure things, and they would weigh them. And whoops, let's just double click there. And so they said this is what the particles are: solid spheres that can't be divided into other things, and each element has its own unique sphere that has its own weight and size. Then the Thomson-Plum pudding model again. Evidence this was from things called cathode rays, which are sort of like fluorescent tubes, and classical physics, and the discovery of the electron. And there we have, so the electrons, these guys, potted around. The negative charge is sort of in this sphere, occupying this space. And then the Rutherford model, alpha particle scattering, which we'll do, and when we do radioactivity we'll look at alpha particles. This is more common, what you see as a representation of an atom. You've got your nucleus, and then you've got your negatively charged electrons whizzing around, but the nucleus was still an unknown quantity at that point. We knew it existed, and we knew that most of the mass was in there, and the atom, as you can see, is made up mostly of nothing if the electrons are whizzing around. The Bohr model, looking at spectra. Spectra are the lines that you get when you excite a gas and you look at it, and you can see light of certain wavelengths coming off. And it gets more complicated because the electrons are in all these shells, and the shells have different energies, so it gets much more complicated. And then the quantum mechanical model started to get those shells even more complicated, and we discovered the proton at that stage. And so here we have the nucleus with the protons, and instead of viewing the electron orbitals as sort of like onion skins, it's now much weirder. You have all these sausage shaped zones and donuts, and the real world is a bit more complicated than that even in terms of the electrons. But these are zones of probability of where the electrons will be found, and so they look quite complicated. If you do chemistry, you do a little bit more of this. And so this is how it is evolved. The current understanding here is that the electrons have a zone of probability of where they will be. So the model that we use in physical science, though, so we stop and say, well, we don't really need to know any more than that. You can learn that in physics and chemistry. And so we keep it to an atom being composed of these sorts of things: protons, which are positively charged particles in the nucleus; neutrons, which are negatively charged particles in the nucleus; electrons, which are negative. Did I say neutrons are neutrally charged? I hope I said that. Anyway, they are neutrons, neutrally. Electrons, which are negatively charged particles, and they're found around the nucleus. And so something like this. And there's our nucleus. Ideally, you should have two colours of particles in here: the protons and the neutrons. Now, none of these are drawn to scale either, and when we start looking at the size of these particles and things, you can't really draw it to scale. I'll use a couple of examples shortly of the size of an atom, which might give you an idea, but these are all stylized representations of what an atom looks like. And so this is better because you've got your protons and neutrons in the nucleus, and so most of the mass of an atom is in the nucleus. All the positive charge is in the nucleus, and all the negative charge is in the electrons. And another representation there. Okay. Now, these protons, electrons, and neutrons are called subatomic particles because they're smaller than the atom. And we know some things about them. For example, we know their relative mass. So we don't have a unit for relative mass. It's relative to each other. It's just what they are. And so what we've said is the proton and neutron weigh the same. And so let's say that they have a mass of 1. An electron, it would take 1,837 electrons to weigh the same amount as a proton. So the electron hardly weighs anything relative to the proton and neutron. That's why I said the mass of an atom is in the nucleus, because the electrons hardly weigh anything. But charge is a different story. The neutron has 0 charge. The protons and electrons have equal but opposite charge, so we call that -1 and +1. And there's no unit to that. If you do physics, we discover that charge does have a unit called coulomb, and this number 1 is actually not 1 coulomb. It's 1.6 times by 1 to the -18 coulombs or something. But we don't need to know that in physical science. We can just say an electron has -1 charge, a proton has +1 charge. So atoms, in their classical sense, are neutrally charged. They would have the same number of electrons as they have protons. And that's our starting point. We start to confuse things a little bit later when we start losing electrons or gaining electrons. But when we talk in this early stage, when we talk atoms, we're saying they're neutral because the number of protons equals the number of neutrons. Electrons. See, I get confused even. Just make sure you read this. Sometimes I ramble on. If an atom gains or loses electrons, we have a thing, we can still call it an atom, but it becomes a special atom, and we call it an ion because it has charge, and it can have a positive charge or a negative charge depending on if it gains or loses electrons. Now, because they occur in the nucleus, protons and neutrons are referred to collectively as nucleons. Okay? And we don't teach you the whole picture. Like I said, in physical science we stop. We stop here at the nucleus, and we now know, or we've known for quite some time, that protons and neutrons and even electrons, which is a bit dodgy, because it's only relatively new, protons and neutrons are made up of other particles which are even smaller and are called quarks, but we don't need to know that. Now, the atom is this size here, very, 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 very small. And an example I use is if we made an atom where the nucleus was about the size of an orange. Okay? If we made that atom something like oxygen or lithium or something, the nearest electron would be, let me think now, if you're sitting in the classroom at Newstead College, the nearest electron would be out at the airport. And between the electron, tiny little electron, which would actually be the size of the top of a pin relative to the orange, that top of a pin out at the airport would be the only thing between the electron and the nucleus. And so you can see why we say atoms are made up pretty much of nothing. There's a lot of nothingness in us. But in terms of physics, we have substance because everything combines. But because these atoms are so small, there's so many of them as well. But I start to ramble, which is not good because it ends up making for a long video. But hey, look, we're at the end. And in the next video, number 3, we'll be looking at the atomic number and mass number. So, cheerio!